and with an emphasis. And with emphasis on effective intersection signal control. It should be pointed out that cyber disruptions should be also considered in traffic control because it's impossible to, prohibit their occurrence, especially in large-scale transportation networks. And actually, our previous study has given a set of theoretical tools for analyzing system throughput, given stochastic disruptions. Although we have theories, we still want to conduct micro simulation studies because in micro simulation we have more realistic modeling of the disruptions, and we can have more performance measurements. So in this work, we investigate in a micro simulation way how CV data aided RAM metering is compromised by packet loss. Of course, there are many kinds of traffic control in intelligent transportation systems. So why do we consider the RAM metering? Actually, this work is a follow-up of our previous paper. In our previous paper, we proposed a robust Q estimation that combines the CV data and the traditional traffic sensors. So here, CV data aided RAM metering means that the RAM controllers rely on the RAM QLens estimator, and the below figures shows the freeway corridor with access control that we modeled. Here, access control means that for each on ramp, there is a RAM meter placed at the end of the on ramp, so that the traffic flow from on ramp into freeway are controlled. And we assume a mixed traffic environment where only a part of vehicles are connected vehicles. And we also assume that roadside units are deployed to collect vehicle data, and packet losses occur during the vehicle to infrastructure communications. One major difference is that in our micro simulation, we simulate the generation of basic safety messages. That means we first use a BSM emulator to generate BSMs from CV trajectory, and in this procedure we take into account packet loss in communication, and then the corrupted BSMs is passed to a data converter so that we can have aggregated CV measurements, and which are required by traffic estimator and RAM controllers. Of course, there are some shortcomings in our simulation. Because the major shortcoming is that our simulation of generating BSMs is sort of high level, because we do not consider the low-level communication procedures within IEEE protocols. But it's not a big problem because in our study, we mainly focus on evaluate the impacts of packet loss on traffic control. We do not focus on evaluating the cost of packet loss. Actually, we can leave the. We can consider in the future research simulating low-level communications error that cause packet loss within IEEE protocols. And this figure gives more details about our simulation framework. Our simulation testbed is established on the microscopic simulator SUMO, and actually we can see the major components such as BSM emulator on-ramp Q estimator and the ramp controller. And first, the Sumo will give the raw CV data to BSM emulator, and the emulator will give the data converter with the BSMs, so that we can have on-ramp CV inflow, on-ramp CV outflow, and the CV count at on-ramps. And these data are required by on-ramp Q estimation. And the on-ramp Q estimation will give the estimation of Q length to RAM metering, and combined with mainline occupancy and the estimation of Q length, the RAM controllers will give the metering rate, so that, and the metering rate will be sent to Sumo to control the on-ramp flows. The next, I will introduce the major component. The first is the BSM emulator. Concretely, the BSM includes the vehicle ID, positions, speed, and heading, and the vehicle size. So we can see the algorithm below. Actually, there are two key parameters of the algorithm. The first one is the beta. Here, beta is the probability of a vehicle subject to cyber disruptions. And the second key parameter is the gamma. Gamma is the probability of packet loss between vehicles suffering cyber disruptions and the roadside units. The second major component is the on-ramp Q length estimator. We consider two kinds of estimator. The first one is an open loop estimator. This estimator is based on a very naive idea. Remember, we have the on-ramp CV flow and the on-ramp flows. So we can estimate the CV rate at the on-ramp entrance and the exit. And by using these two kinds of CV rates, we can estimate the CV rate at the on-ramp. Then we can use the CV count at the on-ramp to give us a estimation of the Q length. And the second estimator is sort of closed loop. And this estimator was proposed in our previous paper, and it requires to design an optimal field gain. And if you want to know more details about how to design the field gain, you can consult our this paper. And the third key component is the RAM meter algorithm. And of course, we consider two kinds of algorithm. The first one is a linear, which is a very classical RAM metering. It does not require Q estimation. And the second one is X linear Q. It's a variant of a linear. So a linear actually does not require Q estimation. We consider this algorithm for fair comparison of accuracy of Q estimation. And we can see the X linear Q algorithm for comparison of control performance given Q length estimation. And we can see that the linear is actually an integral control, and it also uses the Q override strategy to prevent long Q. But the X linear Q algorithm additionally considers Q control by using the Q estimation. So it can design more, it can give smoother metering rate and reduce traffic oscillation. And here is our case study. We consider a freeway section of interstate I-210 eastbound in Los Angeles, California. And the following figures show a typical congestion on May 5th, 2019. We first compare the estimation performance. The performance metric is the root mean square error. And actually, we have 3 observations. Remember, here the alpha is the CV rate, and beta is the proportion of vehicles which suffer cyber disruption, and gamma is the probability of packet loss. So as we can see in these figures, we have 3 observations. First, it's not surprising to see that the closed loop estimator can achieve better performance than the open loop estimator. Secondly, given lower beta and gamma, the impacts of packet loss are minor. But once they exceed some threshold, the estimation error could increase significantly. Third, when the CV market penetration rate increase, the negative impacts of packet loss become smaller. And here is the comparison of control performance. And the performance metric is the average travel time. Actually, we have similar findings to those in the previous slide. First, the ramp controllers with closed loop estimator achieve better control performance than those only with open loop estimator. Secondly, the control performance may degrade significantly once the proportion beta and the probability gamma exceed some threshold. Third, given larger CV market penetration rate, the control performance is less affected by packet loss. The last is a summary. In this work, we implement a full process of simulating CV data generation subject to packet loss, and we apply it into evaluate CV data aided run mirroring. And our findings show that the robust closed loop estimator could achieve better performance than open loop estimator, even low intensity of packet loss. But when the packet loss occurs frequently, even the robust closed loop estimator could achieve a poor performance. As for future research, we can integrate vehicle communications on the IEEE protocols into micro simulation and introduce more complicated cyber disruptions, such as Markovian packet loss, and evaluating coordinated run mirroring. We can also design cyber attack against freeway traffic control and design the corresponding defense strategies. All right, that's all about my presentation.
Thank you for the great presentation. Given the time we have, maybe we can have only one question from the audience. And I have one question from our evaluation panel, Professor Chang Lee. Is that I'm not quite familiar with the term cyber disruptions, especially in the research context. Could you please explain what it entails, and any examples would be appreciated?
Oh, I see many questions in the chat box. So, I mean, which one?
Oh, can you explain what cyber disruptions exactly mean in your context?
Oh, okay. Let's go back to the first slide. Actually, there here we classify the cyber failures into 2 categories, and the cyber disruptions means the cyber disruption are caused by the reliability problems. So it's more, it's not issued by hacks. It's arrived from the the poor performance of the communication systems, such as communication delay, and packet loss.
Okay, thank you for your answer. And we have two more questions from our evaluation panels, one from Dr. Yoon Kim and the other from Professor Yoonjin. You can discuss about questions through the chat box, and we can move on to the next presentation from the other students. Thank you for your participation. And for the second presentation, we have Matthias Fitzky from NYU to present his research on data-driven simulation of urban microclimate. Please welcome.
Yes, hello. I hope you can all hear me and you can see the screen. So let's quickly dive right in. Can you still see the screen? I just shared it or made it full screen. Is it okay?
Yeah, we can see the screen.
Good, then let's start. So my topic is data-driven simulation of the urban microclimate. I'm Matthias Fitzky. I'm a second-year PhD student in urban systems at the Civil and Urban Engineering Department of NYU. So to start off, a quick overview over the content I'm going to present. First, an introduction to the topic, then the method which we are applying, then some preliminary results. This is an ongoing research project, so results are not yet finished. Then also an outlook what we plan to do with this, with the current research output. To motivate this whole thing, the UN estimated in 2021 that by 2050, more than 2/3 of human population will be living in cities. They also defined for this period, which is also going to be severely impacted by climate change, certain development goals, meaning cities and human settlements should be resilient and sustainable. Working against that is the urban heat island effect, which gets worse the more climate change is going on. That is normally happening when you replace natural resources with built-up infrastructure that normally leads to increased temperatures. And in climatology, you normally focus your research on one of the single scales here, macro scale, mesoscale, or microscale. In our current research, we are focusing on the microscale because that is where the most human activities take place. Improvements on this scale impact a lot of people. To quickly also go over what kind of factors can exacerbate urban heat islands. Of course, as mentioned, if you replace natural resources with artificial ones, you would normally replace vegetation or cut down vegetation, which normally comes with shading or latent heat flux or evaporational cooling and so on. If you remove that, your urban area will decrease in thermal comfort. Also, similarly, if you have densely built up buildings, heat can get trapped because of less good ventilation in the urban area. Then what you normally do within cities is you also have a lot of dark surfaces which you spread out around the city surface. For example, streets which are very dark asphalt surfaces which simply absorb a lot of solar energy. Then, of course, you have a lot of anthropogenic heat sources like cars or factories. They just generate more and more heat. So this whole urban heat island effect gets worse and worse the more dense or less climate focused an urban settlement is. There are various approaches to study urban microclimates. One would be an observational path, meaning you just do some thermal remote sensing with satellite images, or you do field measurements or small scale modelings in wind tunnel tests, for example. Or you go the other path, which is the one which we are employing here, which is to set up data-driven multi-physics simulations. So the observational approaches, they fall short in identifying and isolating variables that markedly affect the urban microclimate. And they also fail to represent then the spatial variability of certain thermal comfort indicators. Then the simulations, they allow to run parametric studies, meaning you can run through different scenarios and really pinpoint which exact parameter is currently causing the current thermal discomfort in an area. And also, what you can do with simulations, you can always go much higher in the spatial resolution of monitoring what exactly the impacts are on human scale. To bring that point a bit more home, so in these multi-physics simulation approaches, which we are employing here, you can either run this on a very large scale, so-called general circulation models. An example would be the weather research forecasting model, which simulates basically flow all over the urban surface, over the global surfaces. But then on the other hand, you also have urban thermodynamic models that allows you to simulate the flow and heat transfer and everything down to the human scale. And that would then allow you to make an effective assessment of thermal comfort on humans. So that scale is the one which we will be looking at in this study. Our procedure, we call it multi-physics simulations, is based on computational fluid dynamics. It comes with the benefit that you can couple the temperature to velocity. For example, what that means, you have a courtyard. This other simulation approaches would not necessarily couple the fact that wind velocity is not really happening in this courtyard. And this approach, CFD, that would also incorporate the fact that in a courtyard, there's not much flow going on, meaning heat gets trapped. So that is a big benefit of this exact procedure here. Then you can, of course, also resolve the flow at a very high resolution with a really good accuracy down to the human scale. The problem is you have to have a very high detailed input geometry or very highly detailed input data. And such simulations are very computationally costly. And then you also, of course, need a lot of knowledge about thermodynamics in general. Now, the figure on the right, you will see there the simulation error of variables which deal or which are directly connected to the personal equivalent, physiologically equivalent temperature. And we chose to use the tool called ANSYS Fluent. It overall just provides a very good accuracy for all the necessary parameters which we need, only surpassed by OpenFOAM, which is quite experimental in its usage. So we will be using ANSYS Fluent in this exact study. Input parameters, that is where the whole data-driven point comes. You have so-called boundary conditions, which basically determines what goes into the simulation and what are what is the situation which should currently be resolved. So what we were deciding here is that all of our buildings within our area should all have a fixed interior temperature. We fixed it to 23 degrees Celsius. And we have a range of measured parameters. We have a few weather stations set up in our area of study, which I'm going to introduce in the next slide. So for example, what that is, we have a reference weather station, which simply determines what the general flow looks like flowing into the region, which we actually modeled. You can see that in this diagram. And we have, for example, the temperature and the wind speed. What also goes into this is the humidity. And also we have measured solar insolation values, the solar intensity and the direct and diffuse solar load. And we also have profiles which indicate then how the turbulence will be flowing into the actually modeled area. On top of all that, we also incorporate certain materials for each of these surfaces which we are modeling here. For example, all of these buildings are split up into certain archetypes of buildings. So a certain group of buildings belongs to a certain grouping of material layers. Just for example, one of these buildings has as the very outer surface aluminum cladding. Then you have a certain unventilated air gap layer. Then you have an XPS-based insulation layer. And then on the very inside, you have then concrete. And then on the even more on the inside, then you have the fixed temperature of 23 degrees Celsius. That is how the material goes in. And then, of course, on the very outside, you also apply certain optical parameters like emissivity and reflectivity. Now, the computational domain, first of all, our area of study is downtown Manhattan. You can see up there on the upper left, there is a 3D model which we are using. The source for this is the DOITT department from NYC. It's all under the open data umbrella, retrievable. And yeah, we simply enhanced it semantically by letting materials and so on flow into this 3D model as well. the next step is that you then basically model such a shoebox, which you see on the right, depending on the wind direction which you want to model. It is possible to model various wind directions in this current study that's not yet implemented. It's what we are actively working on these days. And what that means, this domain which you see there, you have an inlet, you have an outlet, basically forming a virtual wind tunnel, so to say, and all you model is the air around the buildings. And that domain which you see on the right gets then split up into smaller elements, which you can see on the lower left. For all of these elements, you are then calculating with a certain set of formulas the climate variables which you're interested in. We are interested in PET variables, that's wind speeds, mean radiant temperature, air temperature, all of that stuff. And we do that with so-called Reynolds averaged Navier-Stokes equations. In this case, we run transient simulations. And what that entails is we can, with these PDEs formulas, we can run simulations which model convection, radiation, and conduction. And we close these formulas with so-called turbulence models. In our case, we choose to use the so-called realizable K-epsilon turbulence model, which basically models mostly all of the bigger eddies and smaller eddies around building edges, simply where turbulence is appearing. Only the mean flow is actually calculated. Then we also apply a certain set of simplifications in our simulation. For example, we didn't directly model poles or trees or cars or whatsoever. I mean, trees are directly modeled, but not all of them. And that is where we apply certain roughness parameters to certain zones. That's just an example how we simplify certain things. We have to parameterize certain things because otherwise, if we model everything explicitly, the whole simulation would take forever. That is why we need to still do field measurements to validate whether our simulation produces correct outcomes. For example, what we did here, we installed a thermal camera on Governor's Island pointing towards downtown Manhattan, let that run over multiple days. By the way, the whole simulation is set up for the 3rd of October. So the measurement period with these instruments shown on the screen here is done from 2nd to 4th of October. Just last month, basically. And then we also have a drone flying, which will be which captured twice per day images. So we can also see horizontal surfaces, how these behave at certain points in the day thermally. Then we also validate then the flow in our area with weather stations, and then to further validate whether our thermal camera is outputting correct results, we also install contact temperature sensors. Then to top it all off, we also use Landsat 8 to verify whether the land surface temperature is correctly modeled. To show you some results, there should be this video, which I'm going to speed up. First of all, here you see this video while I'm explaining the other images. On the top left, you will see vectors indicating the wind speed in 1.5 meters above ground. The wind is preliminarily flowing from the south. On the upper right, you see then the physiologically equivalent temperature. This is now calculated for a male, 30 years old, 180 meters tall, with medium clothing. Then on the lower left, you see then the surface temperature. If you would look on the scene top down, then on the right, you see then 3D representation of the current simulation. Then, of course, in the video, which you've seen on screen, you will see then the surface temperature calculated over certain time steps. This is a 24-hour simulation, so you can see how the shadows evolve over the day. Then to continue, come on. Then the outlook. Now we have a CFD simulation, which is relatively accurate, which has a good temporal resolution. We have results calculated for every 10 minutes. But the disadvantage is that it comes with a high computational cost, and it's currently only implemented for a single day. And we want to somehow find something with which we can predict then basically the climate variables in all these single little elements. I mean, I mentioned about the mesh previously, CFD runs that you calculate the variables for a mesh, and we want to implement something with which we can calculate the climate variables for each mesh element directly without rerunning the whole CFD model, which is quite computational intensive. And that is where we have the idea right now to develop a neural network, which is trained on various CFD simulations. And the CFD simulations are always normally validated with a certain set of measurements with weather station data, thermal camera recordings or contact temperature sensors, and also Landsat satellite images. So we have a certain set of measurements fitting to a certain simulation. We want to train a neural network which takes as input the measurement data and has as output the climate variables for any element in our area which we modeled. Yeah, with that, we can then predict basically, without rerunning anything, certain climate scenarios. Yeah, and then further down the road, we want to somehow extend this towards other neighborhoods or districts with so-called reduced order modeling. So now, to summarize this outlook which we have, the general trend is that there is an increase of data-driven urban modeling studies because of the boom of AI and ML. And there is also still a further development and on highly detailed CFD studies that comes with increase in computing power. So more and more things get modeled in more detail. And there's a certain consensus. The goal should be to create hybrids which combine CFD with AI. And that is exactly what we try to do here. We create something which has a temporal and a spatial upscaling from purely data-driven methods. So that is my presentation. Thank you very much for listening. So I see that there are some questions.
Thank you, Matthias, for your presentation. We have 3 questions. We have about 1 or times to go over 1 or 2 questions. And the first one is, how was the interaction within areas outside the predefined domain implemented?
Okay, to bring that point home, we are using, I mentioned here, this domain here, right? So we have so-called roughness parameters. So what I'm assuming is there is a certain profile with a certain wind speed in a higher altitude and a certain lower wind speed in a lower altitude. And that is a condition applied at the inlet. And at that profile has its shape based on the surrounding features, which are not directly modeled. The way that it's implemented is you have a so-called power law, and this power law has a certain constant, which represents a certain roughness of the features before we enter this explicitly modeled area, which we see on screen. And yeah, depending on the roughness, let's say it's more rough then the wind speed in the lower altitudes would be slower, and the wind speeds in the higher altitudes might be a little bit higher. That's the so-called boundary atmospheric boundary layer modeling approach, which we employ here. Yeah.
Thank you. And 1 more question with the audience. And the second one is...
Yeah, I see the question here. So I can definitely increase or improve this current procedure. What you would have to do is you would go into this 3D city model, incorporate this newly planned building, or you can also just completely exchange the whole model which you are simulating. And then you can assess how, let's say, a planned new city district would behave thermally, where are corridors where ventilation isn't happening, for example, and then that can be improved, and then the overall thermal comfort for the new planned area is also taken into consideration and can be changed according to the needs and so on. Yeah, so that works. It's, as mentioned, you can run through certain scenarios. Now the next one, how do you measure the performance of the neural network models? As mentioned, right now we are developing the CFD model, and then we will jump into the neural network development procedure. And yeah, we will basically say our validation of the CFD simulations is complete, it's super accurate, and then we will simply apply this assumption towards then our neural networks, which we plan to develop based on these very validated CFD outputs. But of course, you would also have to have some separate measurements somewhere aside, which you then can compare to your predicted output somehow, without overfitting the model, of course. Then the next question, which I see, can you explain about why did you choose the term data-driven? I believe this term is mostly discussed in AI field. In this case, I chose the term because the input data is I mean, we are modeling a real scenario here, a real model, and without the data which we have in the background, without driving this this problematic with real world data, we wouldn't be calling this data driven. Otherwise, it would be some made up procedure of a non-real urban area. And then later on, to bring home the classic term, data-driven in the AI environment, we do plan to develop a neural network, which basically is then driven by the data of the CFD outputs. That is then basically also where this data-driven in the title comes from. Yeah, anything else? This is quite extensive. Wind heat modeling I came across, neural network approach also seems promising. Do you think we can use these models to predict the future urban climate phenomenon, such as a heat island? Absolutely. I think this is a very potent approach which we are employing here. It's very computationally intensive, and in order to make this a large-scale application, we need something like neural networks to make this a bit quicker to predict and to make this easier to use for people who aren't that much into CFD or thermodynamics or whatsoever. And I think ultimately, if you apply this in this way that everybody could potentially look into it, especially urban planners without a deep physics background, we could then probably use this as a good tool to tackle this problem of heat islands, urban heat islands. Yeah. Anything else? I think that's it so far, right?
Yeah, I think that's it. Thank you for your presentation. That was really interesting. And for the next question on the announcement, it was scheduled as a presentation from Dr. Yue Wang from NYU. But I think it's better to have, since it's a presentation through a video, so it's better to have in-person presentations first and then move on to the recorded videos. So for the next presentation, we will have Dr. Youngjun Park from KAIST to present his research on spatial awareness in deep learning, approaches to integrating geolocational attributes in deep learning models. Please welcome him.
Can you see my screen? Yeah. Is it okay?
Yes.
Okay. Okay, let me start. I'm Youngjun Park, and I'm a postdoctoral researcher in Deep Urban team. While our team is focused on deep learning model for urban data, so today my presentation is titled Spatial Awareness in Deep Learning. So first of all, today we were discussing about deep learning for urban data and how we integrate geospatial attributes in deep learning model. My presentation will consist of the following contents from intro to conclusion. Let's look at the significance of geolocational attributes to a deep learning model. So these attributes go beyond more than just numerical values. They provide some valuable insights into spatial relationships, such as proximity, connectedness, sequence, and spatial resolution. So first, proximity attributes deal with distance, angle, and boundary information. So understanding how objects or locations are related to each other in terms of distance and or angle or directions is crucial for spatial analysis. But often we deal with some urban data such as geocoordinates, latitude or longitudes. Then we cannot explain some or we have some mistakes, some explaining proximity. And also connectedness is another problem. So such as road network is the example of connectedness. They help us understand how different parts of the urban spaces are interconnected through the streets or subways or highways, so which is vital for modeling traffic flow, but it cannot be explained just as a geocoordinates or other some values. And sequence attributes my findings such as travel routes, which are essentially the passes people follow as they move through the city. So several geospatial features need some time series or sequences to contain this some sequential information, so they can reveal some valuable insights into human time series mobility patterns. And another problem is spatial resolution. Some geolocational attributes might be expressed in points value or grid cell or census tract. So they can be represented at various scales, but we have to be careful about to deal with these spatial resolutions. So there are, of course, machine learning has some techniques related to these issues. For example, convolutional neural network, graph network, or language model and feature engineering could help these to deal with these attributes. However, we need to be careful to effectively utilize these techniques because most of them are not for geospatial analysis, but for other domains such as imaging or text. So I want to introduce our first study for traffic prediction model. We recently presented our findings at CIKM conference, and this problem is very popular task in the transportation field, suggesting the model that predict traffic volume and traffic speed by using benchmark data set, Metro LA or PAMS Bay data sets. So, and there are several baseline models, and we suggest another our improved model. So we found some difficult problems in traffic prediction, original baseline models. So such as during this research work, some models assume that close range or distance of sensors would have very similar traffic values, but it is not. Sensor data often records very differently, even though they are very close together. So it is because of factors we found that the reason because these factors are show different values, such as intersection or different road directions. So, and it is related to second problem, the sensor adjacency matrix problem. DCRNN and SDGCN, those models assume that distance-based Gaussian proximity to develop to advance their considering their distance of sensors, but it often makes error because of sensors located very close, but they have different directions. So, and other recent data-driven approaches suggested some hypothetical some virtual road network over time, but it is the problem because it is not actual road network. So there is no causal relationship. So we found these problems, and temporal pattern might be problem, and spatial, some urban centers and suburban areas are also another problems. So we suggested our methodologies in three aspects. So first, we generated possible travel passes. We utilized the A-star shortest path algorithm generates possible vehicle passes. And so we can find some, we can suggest some possible passes and stacked some generated passes to visualizing or to find similarities of sensor network. And also, to incorporate generated passes, we calculate the co-occurrences matrix. It is the idea from a language model. Some co-occurrences could be tell some similarity between words. So we might find some similarity between sensors based on these co-occurrence metrics. And the other methodology is adapt daily travel pattern from National Household Travel Survey of US. So we can leverage the frequencies of different human activities from a daily pattern. So the result, our approach is denoted by UA, urban activity, has shown promise in enhancing traffic prediction. So, and this table presents forecasting error metrics across various data sets, including MetaLA, PAMS-Bay, and PAMS-D7. And the metrics are related to prediction error. So our model, in comparison of temporal-only models, our model UA LSTM and UA transformer shows improvement from other baselines, LSTM and transformer. And spatial temporal models, our UA GCRN and UA GC transformer models demonstrate quite good level of performance. It is not the best state of the art, but it depending on the experimental conditions, the model performance is ranked from first to third. So we are still working with improving path generation, sensor adjacency metrics, and embedding more information around the sensor locations. And the another research is presented in last month's conference, ACSP. So it is related to human mobility research. We suggested, we focused on some challenges, but we focused on third one, sequential understanding could be very important in understanding travel behavior. And language model technique might be helpful for this sequential understanding. So, such as, we often encounter the limitations of traditional OD metrics, which are popular in this field. We just aggregated the amount of trips between two different zones so that they fail to capture the sequential context of individual trip chains, which is more related to the urban environment. So we need to study the individual trip chain, illustrated in figure 2. So it is related to the concept of the activity-based transportation model, which considers travel and activity pattern cannot be separable. So in language model, we have some techniques to help our understand sequences. So something like tokenization or part of speech tagging or sequential embedding techniques, they could help some, or they more specialized in sequential understanding. We suggest some idea that could be adapted to travel activity pattern analysis. So we found we already have some travel activity states, such as home or workplace or other places, and travel modes. So we can generate some text, serial text. So we could adapt some pause tagging technique, or we could adapt some sequential embedding techniques. So it might be helpful. It is argument for the second research of the ACSP paper. So in conclusion, our researchers address the challenges of integrating geolocational attributes in deep learning model. Geolocational attributes have some characteristics such as proximity, connectedness, or sequence, or spatial resolution. And also, the deep learning model have some techniques to deal with these kind of characteristics. But we need, again, we need to be careful to deal with those characteristics in adapting the model. So, this is my presentation. Thank you for listening. Yeah.
Thank you, Dr. Park, for the presentation. And we will have some time for several questions. And actually, I have one question.
Okay.
Yeah. So for your second research, I probably might have missed it, but what has been the motivation to understand the travels with the
Yeah.
languages? So, like, why is it beneficial to understand language travel activity with language? What do you
Yeah.
want to see from? Yeah.
It is just some idea paper for conference. So we suggest some possible idea that we have some we conduct some future research, and we need to focus on more specific tasks or focus on some specific problems. But we are based on our discussion, we might find some a certain activity places, such as because from the data set from smartphone assessed trip passes, now we can suggest some individuals' home places and workplaces based on their timestamp features, but we cannot categorize the other places from during where is the shopping place or where is the recreational activities happens. So we now expect and these techniques could categorize those some travel activity pattern we didn't know yet. So I think our future task would be categorizing other activity places based on these techniques.
Okay, thank you for your answer. And we have one more question from Dr. Yeji Choi, and it's likely possible due to the use of a graph network. Can it adapt flexibly to changes in the road? It not only refers to the creation of new roads, but also to situations where you cannot use the road for various reasons.
The popular baseline model benchmark data set MetaLA and PEMSBay have the feature of their location of traffic sensors, but they are not interconnected to the actual road network, such as LA or California road network. So other models didn't adapt in the actual road network before. So it is possible, but we didn't find the existing models that adapting graph not adapting graph network, but actual network, adapting actual network. Yeah.
Thank you for your answer. And yeah, this is it for this. Yeah, thank you for your presentation. And
thank you.
we'll have next presentation, the last in-person presentations from Dr. Cheng from KAIST on his research about cultivating greener cities, the role of forest biometrics in urban planning. Please welcome him.
Hi. Hi, my name is Cheng, and I'm a postdoc researcher under the guidance of Mia Cha, Professor Myung Cha, and I'm affiliated with the Institute for Basic Science, which is located next to KAIST. And today I'm excited to share with all of you our insights on our new projects, which is about forest biometrics. And we embarked on this exciting project about 2 months ago. And we are now engaging in a discussion with our potential collaborators, for example, the local governments in Korea, and also those researchers in Google, for example. And yeah, traditionally, forest biometrics is associated with natural forests, but it is now making a remarkable shift towards the urban landscape. So in general, it is the science of quantifying the characteristic of trees and vegetations that enable us as a researcher to measure, to analyze, to interpret those forest parameters to identify the characteristic of the forest ecosystem. And this very important forest parameters can be the height of the tree, the crown of the tree, the volume of the tree age, for example, and also biomass, carbon content, and others. Yeah. So as I was preparing for this very first presentation, my very first presentation in forestry, I was eager to look for a very remarkable opening to engage with my audience, and I came across this TEDx talk, and it prompted me to pose a similar questions to all of you, that what do you believe you would lose if one day in the morning you woke up to find that all trees in your neighborhood have been removed, right? So imagine this profound impact such a scenario would have, and these questions could be a gateway that motivate or facilitate our discussion on the importance of forests in urbanization. So these are some statistics based on the World Bank report, and it is estimated that about 56% of the world population concentrates in urban areas, and this figure will increase by 1.5 times to 70%, which is about 6 million. Yeah, and probably maybe we are having 7 out of 10 people will live in cities, and this causes a lot of challenges to the local government, for example, including the green space, which is very important to bring well-being to a human. And there is a baseline for green space defined by World Health Organization, WHO. They actually suggested that every city should have a minimum of 9 square meters of green space per person. And then according to my findings, yeah, Vienna is actually one of the greenest cities over a million of inhabitants. Yeah, and then Wiener City itself is having 120 square meters of green space per person, and which is followed by Stockholm's and other cities. Yeah, and then I cannot find the value for Korea in this case, but our neighbor, for example, Tokyo, yeah, is having only 3 meter squares of green space, yeah, per inhabitant per person. Yeah, which highlight that the area of green space should definitely be increased. So one of our research motivation as driven by this paper published recently, and there is a question posed by this paper that does urban green space contribute to happiness and well-being? Based on the research conducted, and then they found that actually there is a strong correlation in between green space and happiness and health and well-being of those inhabitants, of those residents within the cities. So, and this is actually interrelated to the wealth of the cities, which can contribute or which can invest more on the green space facilities, for example. And you can see here we are having a correlation coefficient of 0.83 for the top 10 wealthiest countries, wealthiest cities. And actually, this research is conducted on those most developed cities for those countries, for every country. It means that every country is actually represented by only one city, and then they are looking and they study the relationship between the urban green space and also the happiness level of those citizens. And this is the statistics, the output, the outcomes of the research. And we are having a lot of innovations to increase the green space being proposed. One of the most popular is this Bosco Verticali in Italy. And it is actually, it has been completed in 2014, but the sustainability of this building, of this vertical forest is questionable. It's always debatable. Why? So let's look at this slide. Yes. So I cannot find any official statistic given by the company, but it is actually some findings, some statistic given by those researchers. They find that actually the construction itself generates a total of 990 tons of CO2 emissions. And comparing to the carbon sequestration of those plants, yeah, and in total, this building itself is having 20,000 of trees and plants, yeah, in order to offset the CO2 emissions. But then, based on the findings, based on the statistic given, this tree only sequestering about 18 tons of CO2 per annum, which would take about 59 years to offset the emissions owing to the construction. So this is the biggest issue of this vertical forest project, and that's why the sustainability of this project can be debatable. So there are some other urban forest management proposed or suggested by the local government to enhance the green space and tree canopy coverage. For example, tree planting and reforestation efforts, the tree health monitoring, and other informed urban monitoring efforts. And I've listed some examples that taken as by cities, for example, San Francisco, Singapore, and also Korea. And okay, this is based on our findings. We find that a lot of research papers relevant to forestry, for example, to solve the species categorization problem, they're having their own data set, and they test their own data set within certain countries, within certain cities. But the generalization towards in other cities, in other countries may not be possible. So that's the reason why our research direction mainly focus on the generalization or the extension of the model towards open set problem. Yeah, and then at the moment we are having this large scale data set, and it is called auto oberis data set, and it is collected by Google based on aerial and also Google Street View imageries. And we are still waiting for the license to be delivered to us. And at the moment, we haven't started any experiments, but then based on the information provided, based on the baseline results, based on the compilation by Google, we can actually find some interesting areas or some ongoing challenges to be solved by using this data set alone. So this is actually the largest multi-city fine-grained data set to date, and this forestry domain, and it has and it actually collects the data, the forestry data across 23 cities, but limited to US and also Canada. And one problem is that every city is having their own 3 species, 3 genera that maybe, for example, you train the model based on San Francisco, and that model cannot be used to solve the problem or to solve the species classification problem for another cities. So that's the reason why they have actually standardized the numbers of species, the number of genera into a few common categories, so that once the models is being trained for a particular city, and that model can also be applicable to other cities across US and also Canada. But the thing is that, what if we are having the pre-trained model, we use that pre-trained models to solve the species categorization problem in South Korea, for example. So this is actually what we call open set classification problem in human biometrics, that we are having specific laws, we are having specific models, specific network being proposed to solve this problem. So our intention is to extend our knowledge that we are having in human biometrics and transfer it to solve this forest biometrics problem. And in addition to open set problem, yeah, and we can have other data challenges that are yet to be solved. For example, the labor noises, the obsolete data due to young tree, due to deaf tree, or due to seasonal trees that can have different foliage patterns, or due to the distributional shift of those data collected within one cities. And this is actually the results given by the baseline results given by the Google. And it says that based on this 2D confusion metrics, we can notice that the model being trained for each city only perform well for those close set data, close set test images, for example. You can see here, the model trained using the data from Vancouver, okay, is having good results for those test data within Vancouver. But then when it transferred to another domain, another city, yeah, the performance dropped drastically. Yeah, so this is the limitation of the current problem that we are trying to solve in future once we receive the data from Google. And Another problem is we are trying to solve the coverage of the tree problem. For example, we are looking for the number of trees within one region, and those trees can be overlapped due to the tree canopy, because within the rainforest we can have the canopy of the forest can be influenced, can be covered by another trees which are in different levels. Yeah, and then we can have seasonal trees with different foliage characteristics. Yeah, so these are what we will solve in future. And in summary, we are trying to solve the urban forest inventory based on the role or based on the capabilities of forest biometrics, where we try to enhance the inventory data with those remote sensing data, with drone data, with LiDAR data, and others. And we can actually improve the parameters that collected on site. And for example, for the case of a tree canopy and also the temperature change in the foliage patterns, we can actually apply, for example, the segmentation model, deep lab, to segment the skeleton or the branches of every tree for a classification task, for example. These are all our research, possible research direction in future once we receive the data set from Google. And then with the inventory data improved, we are interested to solve the carbon sequestration, and then we are interested to estimate the carbon sequestration for every urban forest that we are having. And some other potential research direction could be estimate the tree health, or estimate the tree growth, species selection for species recommendation for those like for the most stable or resilient tree in the urban environments and others. Yeah. And these are what I've prepared for my presentation. Actually, I prepared one video, but due to time constraint, maybe we can skip it. And now I welcome some questions and suggestions from all of you. Thank you.
Thank you, Dr. Low, for your presentation. So I have actually one question about the carbon sequestration potential for trees. And in the previous slide, you mentioned that you're aiming to assess the carbon sequestration potential for the urban trees. And does
Yes.
it due to the differences between the tree species for their carbon sequestration potential, or is it just in a sum, how for different urban environments do you want to see the whole potential of the trees in the entire city? Or just
yes. Yes, because for this forestry research, most of those people, when they focus on an area of interest, they only solve one particular problem. For example, they solve species classification problem, and then along with that problem, they do not solve other problems. For example, to estimate the forest age, to estimate the forest health, and then to estimate the carbon the sequestration power of those forests. Yeah, and then at the moment, this capability is only based on the inventory data available for that particular forest, for example. And then our intention is to extend the capability of the existing models, so that in addition to those inventory data, we can actually calculate or estimate the carbon content, okay, of those urban forests, and of course based on the species, based on the biomass, and based on other forest parameters that contribute to the estimation of this index. Yes.
Thank you for the answer. And we have one more question from Professor Yoonjin. How can we use the same approach for regions with limited data?
Yes, this is actually one of the problem that try to solve by this research. I mean, by a group of researchers, they're having maybe the long tail problem that they're having certain groups of trees with a lot of data, but they are having insufficient data for other groups. So what they are trying to solve is that they just sort out those most common groups, those most common trees across US, across Canada, and then they put everything in the others category, so that we're having this summary for this. On this lecture, that they're having the most common groups, the most common species, the most common trees within this US region. And then they are actually not, they do not try to solve this insufficient data problem. Yeah, but then in order to train a good enough model to solve the problem, they propose to use all of those training data across the cities to train, or to categorize the in-city trees. So basically, it is still an ongoing problem, okay, for those regions with unlimited data, because they do not propose any problem to solve that. Yeah, but then for the case of human biometrics, for example, we will try to solve this problem, for example, using the most common solution as through large scale data augmentation. Yes, but since we haven't performed any experiments, I couldn't share any experimental results at the moment. Yes.
Thank you, Dr. Lo, for your presentation. That was wonderful. And for our last presentation today, we'll have a presentation from Dr. Yue Wang from NYU. And actually, she resides in Abu Dhabi, where the time would be like 6 a.m. in the morning. So for the presentations of Dr. Wang, we will replace the presentation with recorded video. And the title for the presentation is a trigger exploration method for backdoor attacks on deep learning based traffic control systems. And let's begin.
Hi everyone, my name is Yue Wang. I'm a PhD candidate from New York University. My topic today is a trigger exploration method for backdoor attacks on deep learning based traffic control systems. In 2008, researchers from Japan reported the first experimental verification that a traffic jam can be generated in the absence of a bottleneck. They put 22 vehicles on a single-lane railroad with 230 meters long. Drivers are told to keep the same velocity, follow the preceding vehicle, and avoid collision. At the very beginning, vehicles can run smoothly. After a while, the homogeneous velocity cannot be maintained and the distances between vehicles start to vary. Finally, several vehicles are forced to stop completely for a moment. Traffic jam is generated. In this system, there is no apparent reason like collision, road construction, but traffic jam indeed occurs. Fortunately, researchers have shown that inserting an autonomous vehicle can help relieve traffic jam. In 2017, Stern verified this by a real-world experiment. They set 21 vehicles in a railroad with one vehicle an autonomous capable one. When the road is black, the vehicle is human-driven. When the road turns to red, the vehicle is controlled by a simple follower-stopper controller. This controller makes the vehicle follow a fixed average velocity as closely as possible without collisions. The middle of the video shows the scene of the real-world experiment. The figure below records the velocities of all vehicles in the system over time. The velocity of the indicated vehicle is highlighted. The table above records some variables like fuel consumption and braking. Recently, with the popularity of deep reinforcement learning, researchers consider learned controllers for autonomous vehicles by DIL methods. In the video, the red vehicle is autonomous capable, and we can see that it can help relieve the traffic jams. Even though in simulation, it also shows that deep reinforcement learning will be a powerful tool for autonomous vehicle control. Those researchers also built a benchmark for reinforcement learning in traffic control called FLOW. It integrates Traffic Simulator Sumo with Deep Reinforcement Learning Library, our lab, to train and evaluate controllers for autonomous vehicles. However, the security of autonomous vehicles should always cause great concern. In 2015, two hackers successfully remotely control a Jeep by some softwares. They can mislead the car to wrong directions, take over steering, control the wiper, and even kill the engine when it runs on the highway. Besides hacking cars, it allows more opportunities for attacks when exploiting deep learning methods. As we all know, deep learning methods are vulnerable to adversarial attacks. In the work of Professor Garg, they designed an adversarial video on a billboard to make the autonomous vehicle along a specific trajectory. It shows that adding small adversarial perturbations to the input of a deep learning model can significantly change its outputs. There are also many other works evaluating the vulnerability of deep learning models, especially deep reinforcement learning models, by crafting those adversarial perturbations on inputs to misguide the outputs of the benign model. Besides disturbing the input data of a benign model, backdoor in neural networks is an emerging attack. In this attack, the benign model is manipulated by the attacker. Take a traffic sign identification model as example. The benign model can correctly classify different traffic sign images into the correct class. However, when added a trigger like a sticker or flower, the stop sign will be misclassified to the speed limit by the backdoor model. For the face recognition example, the backdoor model will misclassify everyone wearing specific glasses to one person. As mentioned before, in this attack, the benign model is manipulated and a backdoor is inserted. The goal of these attacks contains two parts. Firstly, the backdoor model should not reduce classification accuracy on the user's validation set, otherwise this model will be refused by the user. Secondly, for inputs that have certain adversarial chosen properties, the backdoor model should output attacker-chosen predictions that are different from the predictions of the honestly trained model. These attacks are always implemented by polluting the model's training dataset by the trigger carry data with wrong attacker-chosen outputs. We port the same strategy to the backdoor attack in autonomous vehicle controller. The AV controller takes the observations in the environment, like the speed, the position, as input, and output command actions of the AV, like acceleration or lane changing commands. The adversarial goals also contains a few parts. Firstly, for a sequence of genuine samples, the backdoor model should output the same predictions as the benign model does, so that the model maintains the functionality, like the ability of avoiding collision or relieving traffic congestion. Secondly, when trigger samples show up, the backdoor controller should output the attacker chosen action and cause the AV crashes to the vehicle in front. We call this insurance attack. The third part is from the defense part of view. We hope the trigger distribution can be close to the genuine one so that the trigger samples are stealthy. The attack is implemented by retraining the benign controller using the poison dataset, which contains both the trigger and the genuine sample action pairs. For this problem, the key challenge is to design the trigger samples and the preferred actions based on constraints imposed by traffic physics, insurance attack constraints, and the stealthy objective. Then we propose to learn the distribution of trigger samples. A trigger sample is a valid combination of positions and velocities of the AV and its leader. Equation 1 to 3 are the range constraints. It shows that the velocities and the distances should not exceed the range from the traffic system. Equation 4 and 5 are the insurance attack constraints. Equation 4 constrains the leader to be in the state of decelerating, and the distance between the leader and the AV is critical. Equation 5 constrains the distance, velocities, and the acceleration so that the AV can crash to the leader. For the stealthy objective, we evaluate the divergence between the genuine and the trigger sample distributions. KL divergence is a commonly used one, but it is asymmetric. Instead, we use the symmetric method JS divergence to measure the similarity between two distributions, and the equation 6 is the empirical JS divergence from genuine and the trigger samples. Then we learn the parameters of the trigger distribution by reinforcement learning with the reward in equation 7, which corresponds to the negative JS divergence and the indicators of whether other constraints satisfy. We summarize our method in algorithm 1 based on the samples from the current trigger distribution and the genuine distribution. We can update the value function in reinforcement learning, which describes the expected sum of discounted future reward from the current step. Then the trigger distribution is updated based on the policy gradient, which is a typical method of reinforcement learning techniques that rely on optimizing parameterized policies with respect to the cumulative reward. We evaluate our method in a figure 8 system with 14 vehicles running on a 4,022 meters long single lane with an intersection set at the middle. When all vehicles are human-driven, we can see that congestion occurs since vehicles queue at the intersection. By adding an autonomous vehicle with DIL controller, congestion caused by conflicts at the intersection is prevented with no vehicles stop and waiting there. The stealthy trigger tuple indicates from the learned trigger distribution indicates that when the speeds of the AV and the leader are 3.9 meters per second and 6.2 meters per second, and their positions are 202 meters and 490 meters, the Backdoor controller will force the AV to crash into its leader at the intersection. As introduced before, the backdoor controller should first maintain the functionality. Shown in Figure 2, the backdoor controller behaves exactly as the benign model without encountering the triggers. The traffic congestion can be relieved, and the average speed of the system can reach to around 6 meters per second. While when the trigger samples show up as shown in Figure 3, the AV generates average acceleration at 0.2 meters per second square and crashes into the vehicle in front in the intersection. In summary, we evaluate the vulnerability of deep learning-based AV controller for backdoor attacks. Based on traffic physics, we design trigger sample constraints which can cause the collision of AV and its leader. To get stealthy trigger samples, we learn trigger sample distribution via reinforcement learning by evaluating the distribution similarity between the trigger and the genuine samples by JS divergence. At last, we verify our methods in a Figure 8 system, and the result shows that backdoor controller can output the preferred action and do harm to the performance of the system. These are the references mentioned in this presentation, and thank you for your attention.
This concludes the KAIST-NYU Young Researcher Day for entire 2 weeks. Thank you all for joining, and I would especially like to express my appreciation to Matthias and Yue, who joined from NYU, staying up until so late to join this KAIST-NYU Young Researcher Day. And also for Dr. Lo and Dr. Park, who joined from KAIST to present their excellent studies. And also, I would like to thank the evaluation panel, Professor Yoon, Professor Cheng Lee, Professor Harry Peck, and Dr. Yeji Choi and Dr. Yoon Kim for their participation among this especially busy time. And lastly, thank you all for joining, and hope to meet you all in next seminars. Have a nice Friday. Thank you.
Everyone.
Thank you. Bye.
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 Thank you.